Okay, this is Projectiles Part 3, and we are going to look at the challenge of determining an angle for a projectile with given information. So let's just draw the title here, Projectiles Part 3, determining the. And another word for the angle that a projectile is fired at is trajectory. So the trajectory is the angle at which we are going to fire the projectile. So we can start off with a simple picture. We'll draw ourselves a reference frame. Well, let's draw the ground like this. And let's draw ourselves a little castle. A castle wall. Obviously, this castle wall has seen better days. And in the castle wall, say here, is a window. And in the window is a little soldier with his bow and arrow protecting the castle. And let's call the height of that window 10 meters. And over here on the other side, you have wheeled up your catapult or trebuchet, and you're about to load it up with a giant rock and swing that rock from the ground. We'll assume it's going to be on the ground. And you're going to try to hit the soldier that's in the window. Okay? So what I'll do on this picture is use a different color, and I'll draw the initial vector. This would be the initial speed. And this time, I'm going to tell you what the initial speed is. The speed at which the catapult can hurl the rock. Let's say we'll make it 40 meters per second. And I will also give you information about how far away you are, or the range to the window. And we have to make sure that the numbers we pick will work. So let's use let's use 90 meters and see if that works out for us. Hopefully it'll work out. Sometimes when you're just picking numbers out of the air like that, you create a scenario that doesn't actually work. It's quite possible that there is no actual way to hit this guy in the window. Maybe this catapult would need to be closer in order to hit him. But that's a legitimate answer too. So if that works out to be the case, we'll be able to see how the math will tell us that. So the other thing that I will tell you is the angle. Well, I won't tell you it, but I will identify it here, and I'll call it theta, which is our mathematical unknown angle. And our job this time is to figure out what is the trajectory. Where would you have to angle this projectile? How would you have to fire it in order to make all of this happen? All right, so we begin by doing everything the same way as we always have. The first step would be resolve the vector. So let's resolve our vector that we've drawn into its components. So I guess I'll use purple since it's the last color. All right, we want to resolve this into the horizontal component, and we want to find out the vertical component. And we know already that this would be 40, the hypotenuse, because it's opposite the angle. It'll be times the sine of the angle. But this time our angle is not a number. So we have no choice but to just throw in sine theta and hope for the best. And there's really not much we can do with that expression, but that still is an expression that represents the initial vertical velocity. So even though it's not an actual number, we don't worry about that. Same happens here with the horizontal velocity, 40 cos theta And again, we don't have any more information about it, but that's okay. And we expect that because if we want to solve for theta, it has to show up in our equation somewhere. Now, we continue through. Let's go down a little bit, and we write our horizontal and vertical equations, as best we can, expressions. So if we consider the vertical motion only, we could look at what the v1 might be, what the acceleration, the displacement, and the time might be. The v1 from our picture is 40 sine theta. And this would have to be a positive value. One of the things that happens when you're dealing with the trig is that if we're using this angle theta, you lose the positive and negative directionality. And in a sense, what you're doing is you're just figuring out the magnitude. This expression right here is telling you what the magnitude is of the horizontal and vertical. This one would be vertical, and this is really just the magnitude of the horizontal. And we've got to watch these arrows so that we know whether they're up or down or left and right. And when we start working with the equations, we may have to put a negative sign in for anything that is down or left. But in this case, up and right means no negative signs to worry about. So, the other thing we know, of course, is our friend gravity is involved. It is the acceleration vertically, so negative 9.8 meters per second squared will be part of the solution. We also know the vertical displacement. The vertical displacement is, again, the difference in height from start to finish, which is right here at Mr. Soldier in the window. And of course, we know that is 10 meters. And it's 10 meters higher than we started, so it would be a total displacement of 10 meters. And of course, the time is unknown at this point. But there's enough information here that we can at least write an expression. So let's do that first. The expression that we're going to write, obviously, if you look at the information here that you're given, it's looking like d equals v1t plus a half at squared. And if we fill in the information we have 10 meters equals, now here's an interesting thing, we have 40 sine theta times t. I have to put the 40 sine theta inside where the v1 is. But I'm going to do this in a kind of a funny way. Don't write this part down, but watch what happens if I just substitute 40 sine theta and then multiply by t. It becomes confusing if the t is part of the sine function argument or if it's a separate term. Now we could put brackets here, that would help, but brackets tend to confuse things. So because it's all being multiplied, it's all of this multiplied by t, one of the things we can do is just write that a little bit differently. So here's the way we tend to write multiplications when we have trig functions. We write it as 40t, and then we stick the sine theta on the very end, so that there's no confusion right here where the angle is. But it still means the same thing. So the 40 and the sine theta are still part of the same term. So that is how we tend to write that, just for clarity. Okay? And keep losing my pen size. This guy right here. For some reason I have to click around to get him back. Okay. Then we have, if we put the 9.8 in for the A and use the half and the minus all at once, we've seen that this is pretty much going to always turn out to 4.9 t squared. That's pretty straightforward for all the projectiles that we do. Now this is not an equation we can solve because it has two variables, but it is an expression that represents the vertical motion. So we've hit a bit of a wall there, so we just kind of stop, and now we're going to go back and we're going to consider the horizontal motion and see if there's any information there that can help us. With horizontal motion for a projectile, we know it's constant speed, so there's a d, there's a v, and there's a t. And the v is from our picture, right there, 40 cos theta, the horizontal component. So we'll write that here, 40 cos theta. And d horizontally is the range, which is the red line at the bottom here, 90 meters. So we need to go 90 meters sideways in order to make this work. And again, the time is unknown. And so we're stuck with a situation here where we have two equations, but they have the same t in common. The time in the air, which is the t over in this equation, right here and here, is also the same amount of time that the object has to go horizontally. So what we can do is write our expression for the horizontal, d equals vt, 90 equals, and again, I'll do my little trick over there, 40, I'll multiply by the t, and I'll stick the cos theta on the end. It's still multiplying by 3 different terms, so it works. It's just less confusing. Now, the interesting thing about this is that it's not solvable either, but if I isolate for the thing I want to get rid of, I'm trying to find theta, so the t is annoying. It's kind of in the way. So if I isolate this for t, it would be 90 divided by 40 cos theta. And if I wanted to, I could do 90 divided by 40. 90 divided by 40 is 2 point. That'll be 40 going into the remainder of 10, so I'm going to guess 2.2-ish. 2.25, perfect. And of course, the cos theta is still on the bottom. Don't be confused by that. Sometimes people see it and they put it on the top, but it's still here on the bottom of the fraction. So there is my time. And if that's the same time as the time over here, then I can substitute it and replace the t's in this equation with that. So this is the same process. It's just that we have these nasty sine and cos thetas hanging around and we have to deal with them. But that's okay, we know how. All right, so let's do the substitution. After the substitution, this equation is going to get a little bit hairy. 10 equals 40 multiplied by 2.25 divided by cos theta. There's my substitution, and I still have to multiply by sine theta. And then I have 4.9, and then I have to substitute it again, 2.25 over cos theta, and I have to square it. Actually, looking at the equation, if we had substituted this term instead of doing the division, you can see how the 40s are going to cancel. Sometimes it's easier just to throw in this and not worry about doing the simplified version like this. But it won't matter. If we do the math, it'll still work out either way. So let's just crunch it out as we have it. So this simplifies, and we get 40 times 2.25, which probably is 90, right? Because that's what we did over there. We divided by 40. So I'm assuming that's 90. And then divided by cos, I'm going to do every step here at a time without skipping any, times sine theta. Minus, and we have to square our bracket. So what is 2.25 squared? Somebody give me 2.25 squared so we get the right number. 5.068.
2.
Oh, okay. Well, we'll go with the 0.6 then, carry 2 decimal places. And then on the bottom, if you square cos theta times cos theta, we have cos theta squared. And I don't know if you remember from grade 11 identities, we write it like this, and we call it cos squared theta, right? But that just means the square, cos theta times cos theta. All right. Let's carry this a little further and see what happens. One of the things we can realize is if we look at this first fraction right here, this simplifies to 10 equals 90 sine theta divided by cos theta. Right? And over here, this would be, what's 4.9 times 5.06? Say that again? 24.8. And on the bottom, cos squared theta. Okay. Now on the side over here, I'm going to show you a couple of trigonometric identities, some cool things that happen. If you recall, sine theta is equal to opposite over hypotenuse. That's how we memorized it. And cos theta is equal to adjacent over hypotenuse. So we know this. So that means that if we have sine theta divided by cos theta, that would equal opposite over hypotenuse, which is the sine theta, divided by adjacent over hypotenuse. Right? And the rule for dividing by fractions is to multiply by the reciprocal. And so sine theta divided by cos theta is actually equal to opposite over hypotenuse multiplied by the reciprocal of that bottom term, which is hypotenuse over adjacent. And that means that that equals opposite over adjacent, which is tan theta. So sine theta divided by cos theta is the same thing as tan theta. So we can replace that over here with 90 times tan theta, which makes it a little bit simpler. All right. Now, the other thing we can do is we can look at this other term that we have right over here and look at what happens with cos squared theta. Well, if I just keep my little aside here, 24.8 over cos squared theta is the same as writing 24.8 times the reciprocal of cos squared theta. And you hopefully will remember that there are reciprocals of all of the trigonometric functions. So what is the reciprocal of cos theta? 1 over cos theta is called what? Anybody remember? Secant theta. Remember secant? That equals secant theta. 1 over sine theta would be cosecant theta, and 1 over tan theta is cotangent. You tend to learn those in grade 11 and then you don't see them much anymore, so you forget about them. They drift into your subconscious somewhere, but they're still floating around, aren't they? Now, that means that 1 over cos squared theta, if I just square both sides of this, 1 squared is 1, cos theta squared is cos squared theta, and secant squared theta is what we get on the other side by squaring both sides of that. So that means I can go back to my little equation and I can replace this number with 24.8 times secant squared theta, which again eliminates my fraction and makes this a little bit simpler using our trig identities. But I still don't have something that's solvable because I have two different trig functions. So we have to do one more little sort of a side experiment in our trig. And I'll do it down here. Remember, I'll keep this line here so we don't confuse the solutions. Remember that, I better get rid of that little mark or it's going to interfere. So, if we go back and we say, you have learned that there's a trig identity, hopefully you'll remember this, sine squared theta plus cos squared theta equals 1. Right? And that's the Pythagorean identity because it comes from the Pythagorean theorem applied to the triangle of trig. I have to get my thickness line back here. I have to figure out why that keeps doing that. Okay. So if we assume that we all understand that, I won't go into the details of how that is formed, but if you draw a picture of a line, right, and radius is 1, the unit circle, and you look at the height, which is the two sides of the triangle, we already know that this is theta, sine theta, cos theta, c squared equals a squared plus b squared. You can work that out into that, which you did in grade 11. So assuming we know that, we can do anything we want to an equation as long as we do it to both sides. And so we could, cover both sides in chocolate or dip them in sprinkles or divide by 7 or anything that we feel might be useful. And after a little bit of trial and error, some people discovered that dividing all of the terms by cos squared theta is actually a pretty useful thing to do. So we will divide all the terms by cos squared theta, just for the fun of it. And when you do that, you can simplify sine squared theta over cos squared theta. Well, we said that sine theta over cos theta is tan theta, right? We did that before. So sine squared theta over cos squared theta is tan squared theta. Cos squared theta over cos squared theta is 1. And what's 1 over cos squared theta? Well, we said the reciprocal of cos theta is secant theta. 1 over cos theta is secant theta. So 1 over cos squared theta, this is just the square of that, would be 1 over secant squared. Oh, sorry, not 1 over, my mistake. Let's erase that. It would actually just be secant theta, right? So we're going to have the thick pen again, but we'll just live with it. Oh, maybe not. Secant squared theta. So what this is an identity. It's telling us that we can replace secant squared theta with this expression, tan squared theta plus 1. And that's very handy because up here in I have a secant squared theta. Let's replace it with what we just found. Equals 90. We'll leave the tan theta alone for now. And let's use that identity and replace this with what we had. It was tan squared theta plus 1. So we'll put that in brackets and substitute it, tan squared theta plus 1. Now we've succeeded in creating an equation that only has tan theta in it, or tan squared theta. But that is getting closer and closer to solvable. Let's do some algebra. 10 equals 90 tan theta minus 24.8 tan squared theta, and then minus 24.8, which is times 1. Let's group our like terms. If I move this over to the other side, it will become positive and add to the 10 to make 34.8 equals 90 tan theta minus 24.8 tan squared theta. If I move all the terms to one side, I will end up with 24.8 tan squared theta. And that's going to become positive as I move it over, minus 90 tan theta plus 34.8. I always get a little nervous when the c term in my quadratic equation is positive, because that could mean possibly an imaginary root. And if we do get an imaginary root, it'll actually prove that what we assume might happen at the beginning, where this might not actually reach the castle wall. It could happen. But that's okay, because this is a learning opportunity. But notice what this is. It is a quadratic equation. The first term has a squared variable, and then not squared, and then the c term has no variable. And we can solve it with QRF, just like we would for any other equation. Hopefully you get a couple of examples like this in your math. What we do, if you want to help you visualize it, you can just remind yourself. Let's just say that x will represent tan theta. And if we assume that x will be tan theta, then we can rewrite our equation in a much more familiar form. But this is not a necessary step, as long as you keep your wits about you. 90x plus 34.8 equals 0. And now you can see how close we are to our solution. All we have to do is figure out what that is using our quadratic roots formula, QRF. And this will be the magic moment that tells us if this is going to be possible or not. All right. Hopefully it will, so we can get a solution. But negative b, if you all recall, this will be plus 90, negative 90, plus or minus the square root of negative 90 squared minus 4 times 24 times 34.8. I think it's going to work. All divided by 2a, or 2 times 24.8. Which becomes, now remember, the value of this is x, right? X equals. So we're figuring out what that x is, but that x is actually tan theta. We've got to keep that in mind. So let's keep on going. X would be 90 plus or minus, and if we figure out this next term, we have to take 34.8 and multiply it by 24 and multiply it by 4, which is a fairly large number, but we have to add that to 90 squared and hope that it'll work, and then take the square root. I ended up getting about 69-ish. Did anybody else get that? We'll double check. After you take the square root, that all works out to a nice positive 69. You got what? 68.98 is what I got, so I just rounded up. Is that okay?
It's supposed to be 24.8 under the...
Yeah.
Under here? Oh, right here. You're right, 24.8. Let's fix that. Right there, folks, 24.8, which will make this, it probably won't change it much, but it might change it just a little. So for precision, we'll do it again. 34.8 times 24.8 times 4 equals. And that's going to be a negative number times 90 squared. Nope, plus 90 squared. Here, start again. 24.8 times 34.8 equals plus 90 squared equals square root 68.2-ish then. All right? So we'll fix that. We'll erase this and we'll put it in 68.2-ish. 68.2. And we're still dividing by 2 times, well, we could do that multiplication, can't we? Better erase that. We can do 24.8 times 2 and get what was that, 49.6, right? Okay, so we have two options, and we're solving for, now remember, we've gotten into the habit of using QRF to solve for time, and we've always said, well, there's no negative time, so we don't have to do the negative one. But we're not solving for time anymore. We're solving for an angle, and there it's possible to have a negative angle. So we have to consider both possible solutions. So we can't just eliminate the negative one. That's why it's always a bad habit to just pretend that negative roots don't exist or are meaningless. In this case, they would be. So first, let's do the positive root. 90 plus, well, they'll both be positive roots anyway, won't they, now that I see the math. Divided by 49.6 gives me x equals 91. Somebody can check my math. One possible answer. And then we have 90 minus 68.2 equals divided by 49.6. Or, if we do the minus, we get 0.44. Did I do that right? No?
First one makes 3.
Let's check it again. So it's 90 plus 68.2 equals divided by 49.6 equals, yeah. I think I pressed something funny on the calculator. I'm not used to the cell phone calculator because it's hard to know if you've actually pushed the buttons or not. But hey, we're using a smartboard, so technology is great. All right, 3.2, right? Is that better? Okay. So the positive root is 3.2, and 0.44 is good for the other one, right? Check that one too. Awesome. Now remember, those are not our answers, because x is not what we're after. We have to remember that we're solving this quadratic equation under the impression that x represents tan theta. So actually, it's tan theta that equals 3.2, or it's tan theta that equals 0.44. So, guess what we have to do? We have to finish this off by taking the inverse, or the arctan of 3.2, the inverse tan. And if we inverse tan 3.2, I think this one comes out to theta is about 73-ish degrees. If you round it off, right? And then if we take 0.44 and we do the inverse tan, that comes out to about 24-ish degrees. I'm just rounding off. We have two answers, and we have to figure out which one is correct. Well, it turns out that they are both correct. And the reason they're both correct is if you have a projectile, right, you'll recall that the maximum range you can get is if you fire the projectile at 45 degrees. And that will give you the furthest possible range. It's an important thing to remember. But if you fire the projectile at a slightly larger angle than 45, what happens is you get a higher projectile, but it doesn't go as far. It drops down as far. Right? Now that looks like we've gone quite a bit past 45. That looks more like 70-ish, maybe 75 degrees, right? So let's pick 75, which means we bumped it up here by 30 degrees. Well, if we bump it down by the same 30 degrees, guess what happens? If I shoot at 15, I will also go below, my picture's a bit off, and I will end up landing in exactly the same spot. If I shoot below 45 degrees by the same angle. So there are always two answers. So I could hit the guy in the castle window either by shooting at this angle. If we go back to our original picture, I could shoot at him and I could hit him at two different angles. That's what this is telling me. One of the angles will produce a flight path that shoots sort of below. This picture is kind of messed up, but if we use a nice dark black pen here, let me just get my thing back. Let's make a nice thick black line. And yeah. So one of them would be firing low and hitting them like that, and the other one would be, if we go right up here a little higher, would be more like firing up high and coming down and hitting them like that. Two possible ways to shoot, right? And 45 is sort of somewhere in the middle. So that took a lot of wiggling around of numbers and mathematics, but it used all those trig identities that you learned in grade 11 and probably just put in the back of your mind somewhere, and we'll dust them off maybe 3 years from now if you ever need them, right? But they are there, and you'll notice that none of this math is anything beyond what you learned. It's just putting together all these things in a cool way and using the trig identities to simplify an equation that has trig in it. Trigonometry plays a huge role in physics as you move on. And so learning how to simplify the expressions that you make with trig, which is what we did all over here on this part of the side of the board, that is a useful tool in taking complicated trigonometric equations and reducing them to something that's solvable. So that is how you would find the angle of a projectile if you needed to. It's also an interesting sort of thing to do, to reproduce this solution without any numbers at all. And instead of getting an answer, you might end up with a nice, clever trajectory formula that could produce the angle. I'll leave that with you to as sort of a little homework assignment or a little fun thing to do on the weekend when you have time on your hands. Try this entire solution with only variables and see if you could work out what we would call a trajectory equation that could be used to calculate the trajectory. So that's something that a real physicist might do, so that he could hand that equation to a computer programmer who could program it into the launching software for, say, a missile that the military might use. So that's the end of that.